Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper trending on X, published on March 15th, 2026, just 5 days ago. It introduces a novel architecture using matrix-valued hidden states that improves perplexity by up to 0.5 points on a 7 billion parameter mixture of experts model, while using 3 times smaller state sizes than equivalent hybrid models. The paper is titled M2RNN, Nonlinear Recurrent Neural Networks with Matrix-Valued States for Scalable Language Modeling. And as we'll see later, the architecture shows some really exciting improvements, with significant implications for scaling foundation models efficiently. Well, Figure 1 illustrates the behavior of the forget gate, which controls how much past information the model retains. The gate's value ranges from 0 to 1, where 1 fully preserves the current state and 0 resets it completely. The different curves show various heads in the model, using unique, learnable parameters to adjust their own rate of forgetting. Because this forget gate relies only on the current input, the calculations can be efficiently parallelized across the entire sequence. Alright, Figure 2 details the architecture of the M2RNN layer itself. On the left, we see how this block slots into a standard setup, replacing traditional attention while keeping familiar components like normalization and multi-layer perceptrons. The expanded view on the right reveals the layer's inner workings. The input is projected to form queries, keys, and values, which then pass through causal convolutions. Alongside these, the model computes the forget and output gates. Because all these initial projections depend strictly on the current input, they can be computed in parallel across the sequence before entering the core recurrence mechanism. Okay, Figure 2 detailed the architecture, so Figure 3 now evaluates the models on the S3 state tracking task, which measures the network's ability to maintain complex information over time. The vertical dashed line marks the maximum training context length of 128 tokens, yet the models are tested on sequences up to 512 tokens. While the linear gated delta net fails entirely and the gated delta product degrades after 256 tokens, the nonlinear M2RNN and the gated recurrent unit maintain near perfect accuracy throughout. This highlights that M2RNN generalizes flawlessly to sequence lengths far beyond its training data. So, while the previous figure demonstrated perfect state tracking, Table 2 evaluates a 7 billion parameter mixture of experts model across various benchmarks. The top section shows the standalone M2RNN matching Mamba 2 and outperforming gated delta net on average accuracy. The middle block highlights that interleaving M2RNN layers with attention achieves the best perplexity. Finally, the bottom rows reveal that replacing just one recurrent layer with M2RNN in existing hybrids yields comparable overall gains. Alright, Table 1 shifts the focus to a smaller 410 million parameter dense model. The top rows show that the standalone M2RNN matches Mamba 2 on Wikitext perplexity, while clearly outperforming both Mamba 2 and gated delta net on the Lambda benchmark. Moving to the middle section, the hybrid M2RNN model beats other two-way hybrids by achieving higher average downstream accuracy. Finally, the bottom rows demonstrate that injecting just 1 to 3 M2RNN layers into existing hybrid architectures provides noticeable accuracy gains, reinforcing the overall efficiency of these expressive non-linear layers. Okay, Table 7 breaks down the impact of state size and gating mechanisms. The top row establishes a baseline with a traditional vector-valued RNN. Because the M2RNN, shown in the bottom row, boasts a massive state capacity of over 86,000, it easily outperforms this baseline by over 10 perplexity points on Wikitext and over 280 points on Lambda. The middle row then highlights that even a GRU model, which requires more parameters for gating, still falls short. This confirms that expanding state size is the primary driver of these improvements. Well, Table 7 confirmed the importance of state size, so Figure 10 plots training throughput across different context lengths. The top blue line shows Mamba 2 consistently achieving the highest throughput, while the red transformer ++ line drops sharply at longer contexts because of its quadratic complexity. The standalone M2RNN, shown by the bottom green line, is more expensive due to higher constant factors. However, the brown line reveals that injecting a single M2RNN layer into a hybrid model maintains throughput within 6% of the baseline, which makes it a highly practical upgrade. So, wrapping up, 2 main takeaways stand out. First, nonlinear RNNs are back as a highly scalable building block for foundation models. Second, Using matrix-valued states solves complex state tracking, meaning that adding just one M2 RNN layer to existing hybrids boosts overall performance without hurting training speed. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.